This video is going to dive a little deeper into how intermolecular forces can influence properties of various compounds. Before we get into that, let's review a little bit. The strongest intermolecular forces are going to be covalent network. This is commonly found in diamonds, graphite, silica. This is the repeating network of covalent bonds. Next strongest is metallic, which is found in metals. Third strongest is ionic, which is any compound that has transferred electrons and gained full positive or negative charges that are attracting each other. And then next would be any covalent or molecular compound. So out of the four main things, these are the weakest. Covalent and molecular then are further divided based on their strength. The hydrogen bond here would be out of covalence, the first strongest. And that's because of its polar nature and the extreme partial charges in comparison to other molecules that it can attain. So these strong partial charges allow for a lot of attraction between adjacent molecules. Next, in terms of strength, is going to be normal polar molecules that don't have that H bonded to an F, N, or O, but still have this kind of permanent asymmetry, permanent dipole. So they always have this kind of partially negative end and partially positive end. Then after that, we're going to have dispersion forces. Dispersion forces have the weakest partial charges attained, as they are random, they change, and they're based solely on the movement of electrons. And so unlike a polar molecule where you can count on there being a partial positive and negative end, in a dispersion force, it is constantly in flux. We're going to see that this influences our states of matter as we are looking at things that are solid, liquid, or gas at room temperature. We can kind of get a little bit of information just based on their state of matter about the strength of their intermolecular forces. Phase changes are one of the ways we can kind of look and see what might be happening on a microscopic level between different molecules of a substance based on how much energy it's going to take us to change it into a liquid or a gas. The heating curve is a graph we can use to kind of look at where these temperatures are changing and get some more data so we can use that to predict how strong the intermolecular forces are. The heating curve looks like this, and we have different segments here. So we have our first segment, our third segment, and our fifth segment that all have these sloped lines. And at these segments, the temperature is increasing. The kinetic energy, which is the speed of those molecules, is also increasing. Energy is being put into whatever the substance is in these cases, and that energy is being used to do these things. However, if you look in between all of those segmented lines, we find these plateaus, these flat lines. And in this case, temperature is not changing. And what is happening is these phase changes are boiling and are melting. And that is caused by a change in intermolecular forces. The energy, once you reach your melting point, is then being used to weaken the intermolecular forces, to take them out of their solid crystal structure and allow them to flow, which is weakening their grip on adjacent molecules. And here we find that the energy is being used to completely break the IMFs. Again, the temperature does not change here. What is changing is the attraction between adjacent molecules. Boiling point is going to be a little bit better of an indicator for IMF strength, because when you have the molecules still near each other, For melting point, there are some other factors that can influence how readily they can flow. So starting with solids, we have solids that are going to be the greatest hold of the IMF. The IMFs are holding them in place. The molecules don't have enough energy to kind of break free of that attraction and move around. And so we get these highly ordered crystalline structures. Mostly we think of this in terms of crystalline structures for ionic compounds, but covalent compounds, if they're in their solid form, can also form these crystalline structure. It's simply a repeating pattern of how these molecules are locking into place. As we add energy to a solid, it will weaken these intermolecular forces and allow them to break free of that crystalline structure. This allows them to flow. When they're flowing, they still have attractive forces between them and adjacent molecules, but it's not enough to kind of stop them in their tracks and lock them into their place. As we get into liquids, we're going to see some other properties that we don't see with solids occur because of this ability to move and other things to kind of be submerged within the liquid itself. So one of these properties is surface tension. And so if you see the little bug here is able to float on the water, that is because of the water's ability to have high surface tension. If it were oil or another nonpolar liquid, the bug would not be able to do this as easily. And that's because deep in the liquid, we find that the water molecules have their intermolecular forces, assuming that this is a sample of water, which we will. So on every side of this central water molecule here, there is attraction to other water molecules. However, if we look at the surface of the liquid, there's only attraction to other water molecules that are below the surface. Above the surface, when we have air, there is obviously air molecules. And air molecules are mostly made up of nonpolar substances in their gaseous form. And so the attraction ability for this water molecule here to the air is not as great as the attraction ability to these adjacent water molecules. And so we have this cohesion where these water molecules are kind of holding on to each other. So we see that there is extra strength that they're trying to hold on because they don't really want to make attractive forces with the air. And this causes, as we can see from the little bug floating, the ability of things to float on water fairly easily. Now, there are other factors, buoyancy and things like that. But for example, you can put a paper clip, which is more dense than water, on water. And it's not until you cause the surface to break that it will actually sink. And that's because the strength of the water molecules is actually holding it together. If you think of like the game of Red Rover, it's kind of like you need enough energy to be able to get through those attractive forces. And so water is really strong hold on that. That's not allowing other things to break through as easily. Viscosity, also along these same lines. Viscosity is kind of how easily can these molecules slip past each other. The harder it is for them to slip past each other, the higher their intermolecular forces must be because they are kind of gripping on and causing them to not be able to move as freely. The freer they can move, the weaker the intermolecular forces must be. Another thing we can look at is polarity. If we look at an oil molecule, we would know that this has dispersion forces because it's nonpolar. A water molecule is going to have hydrogen bonding attractive forces. Because hydrogen bonding is so much stronger than dispersion, the attraction between adjacent hydrogen and oxygen molecules is going to be very strong. and adjacent oil molecules is not going to be as strong. And so water is not going to break its attractive force to make a worse attractive force. Dispersion is not going to have as good of partial charges as other water molecules. So it would be a net loss of energy for water to have to break its intermolecular force and make it with something that has worse partial charges. So we find that this means things that don't have similar intermolecular forces or similar polarities don't want to mix with one another. And this is kind of referred to as miscibility. Things that are polar can mix with water, but if there is something that's better, water will again mix with that. Things that are non-polar will not want to mix with water because again, the forces are too dissimilar. As we look again back to the heating curve, we are going then from a liquid into a gas phase. We're going to find that we have to completely sever one molecule from another. So if we're thinking of water, for example, we have two water molecules that have this kind of attraction to each other right here. So I need to completely break that so each water molecule can kind of go off on its own as a gas. And when we have gases, there's really no attractive forces between them because they're so far apart. This will lead to the ability to use boiling point to determine strength of intermolecular forces, because the more energy I have to put into allowing those to sever, the stronger they must be holding together. Again, phase changes then make good indicators of strength of intermolecular forces. Boiling point is better because of the lack of other factors coming into play affecting it. Looking at boiling point, often for covalent dispersion molecules especially, we're going to find that size can play a big role in their boiling point. So all of these molecules are nonpolar. And if they're nonpolar, that means dispersion is the only intermolecular force that they have, which again is the movement of electrons randomly to create partial charges. And so if I look at this one is not going to have that many electrons to create a large partial charge when I compare it with this one. The ability of this one to create larger partial charges is going to increase its ability to have those dispersion forces stick molecules together a little bit better. And so we see that reflected in the fact that octane has way higher of a boiling point than methane. And that's simply due to the ability of octane to create more imbalance in its electrons and therefore greater partial charges, which can attract adjacent molecules. Branching will also play into this. So this molecule here, number one, has way more surface area for those electrons to build up their partial charges than molecule number two. Even though they're the same formula, molecule number two would be expected to have a lower boiling point because it doesn't have as much of an ability to build up those partial charges and therefore attract other molecules with as strong of a force. When we look especially at biological molecules, we oftentimes will find that we can have kind of multiple parts of a molecule. So we get a long carbon chain maybe at the end that's nonpolar, and then we get a polar part of the molecule that can do hydrogen bonding. So here we would have hydrogen bonding on this part, but we can have dispersion on this part. And again, this is commonly seen in a lot of biology things. So if you think like lipid bilayer, why is it letting hydrophobic and hydrophilic things through? It's all because of intermolecular forces. If you've ever heard of micellar water, that's essentially the same idea. It's gonna surround nonpolar dirt, and then polar water can wash it away. That's the same kind of theory behind soap as well. So there's a lot of uses to molecules that can have a polar area and a nonpolar area, because it allows that like dissolves like part to exist with anything that can either be polar or nonpolar. Looking at this chart, we can kind of summarize a little bit of what we talked about. Molar mass is a way to identify electrons, and it is just adding up the numbers from the periodic table. So carbon's molar mass is 12.01. Hydrogen, there's 4 of, and it's 1.01. So if I add those together, the molar mass of CH4 is 16.05. Similarly, we can do water. So water is hydrogen again. There's 2 of them, so 2.02. Oxygen is 16, so water would be 18.02. Really, we're just looking how many electrons they have, but because molar mass is such a common thing used in chemistry, you'll oftentimes just see people reference the molar mass as a quick way to see, okay, which of these is going to have more electrons, which one's going to be bigger. Then we also have to look at the primary IMF. That's going to be the strongest intermolecular force it has. In the case of CH4, that is going to be dispersion, because it is nonpolar, and nonpolar things only have dispersion. Water is going to be hydrogen bonding, because for both of these, they're covalent compounds, but water is a polar molecule, and specifically it has an H bonded to an O. Looking at the rest of the chart, then, we would be able to kind of determine, based on the primary IMF, using the size as another justification, and a boiling point to aid us in our relative ranking. So looking at just all these boiling points, we can see that iron is obviously the highest, and iron would have metallic bonding. So that makes sense. This would be the highest out of all of them in terms of intermolecular forces. So I'm going to leave you to try these problems on your own.